All right, let's get started. Oh my goodness, the ranks seem to have thinned today for some reason. Very interesting. Okay, before I ask for questions and things, a couple of remarks. So I've looked at some. I've had occasion to look at some project code, and I have to strongly suggest that you work on readability. Are your statements all crowded together? Do your lines continue for hundreds of characters? This is not good. So I mean, you'd hope that since the target of our compiler is Python, that people would learn to keep things properly indented. But no, it doesn't seem to work. So we do consider such readability issues in our grading. Let me also say that I noticed that a lot of your rules get quite complicated. Now, I've done this project, and I found that the vast majority of my rules look like, they look like, sorry about those those of you taking from the screen, I'll read this to you. They basically look like something like, I don't know, an E is a foo followed by a bar followed by a baz, and then they either say something like maybe this foo is foo. So either they're like this, meaning that I use the default tree. In other words, E goes to foo caret bar baz, meaning some sort of tree structure, or they look like this, E foo bar baz, and $$ equals $caret $star. And maybe there's some punctuation in here, for example, that I get rid of with an exclamation point, and that's about it. Most of the rules look like this. And that's just, it's just a matter of making sure that, there better be an operator in here, let's say a thud. Most of my rules look something like that. And that's what all this mechanism is for. It's so that you don't have to go and do things like that. So please bear that in mind. This is a very powerful framework. And as I say, it resembles, you'll find others like it out there in the real world. Among other things that's kind of nice is that if you have a particularly complicated right-hand side, where it makes sense to group a couple of these things together and have another non-terminal for them, that will work. And if you don't give a rule for them and you don't give an operator, then just that list of operands will be goes back and gets spliced into the right-hand side. So it does most. I was actually kind of surprised myself. It does a lot of the things that you really want. And now also let me tell you a little trick that you might find useful. I won't tell you where you might find it useful, but you might find it useful. And that trick is, well, actually it's by means of a hint, I guess. You know that we have these exemplar things, which when you define them, it's basically a trick that causes the program to record that such and such an operator goes with such and such a class. So it does that pretty nicely. So there are actually two tricks. The first trick is to recognize exactly how that works. It works by calling. The exemplar serves as an object that can be stored. by the system, and that has a method in it, a make method that makes new objects of the same kind it is, or makes new objects anyway. So the first hint is that that make procedure doesn't have to be the way that we showed you in the example. In the example, our make procedure is just haul off and call and do a new on the class that they're in and return that. You don't have to do that. Your make procedure can actually do anything that returns a node. So, for example, if you had I'll just say that. And your make procedure can do anything that returns a node. That's the nice advantage. That's the nice advantage of factory methods. They do not require that they don't bind you to the particular class you're in. You can do anything you need to do. The other thing is, there's no reason why you can't have more than one exemplar for a class. So you can have an exemplar that you can use the same class, you can reuse the same class for two different operators if you want. I'm not saying why that would be useful. I'm just telling you that you can do that because that's the machinery doesn't prevent it. So as long you can't have two classes for the same operator, but you can have two operators for the same class. So if you combine that insight with the make insight, you can actually clean up certain of your trees if you want to. You don't have to do it this way, but if you want to. I'm not going to go any further in this because I'm not suggesting you have to do this. I'm just putting out there as a hint for the receptive amongst you, right? So the unreceptive, that's fine. You can just go and do things by hand and it's okay. But the receptive, I just put this out for you and I'll be curious to see whether anyone picks it up. Okay, questions? Yes?
Are there any requirements on the readability of the AST to the
output? No. I don't care what it looks like because I'm not going to read it. My programs are going to read it. And I don't have time to put aesthetic sense into my programs. Well, not most of them anyway. In fact, if we were actually seriously using textual ASTs to transmit data around the program, which, by the way, is not a terribly good idea in the real world. But if we were to do that, then I'd probably produce an AST with as little white space as possible. And just cram everything together. In fact, I'd probably require that there be no extraneous white space, that the white space all be in predictable places. And that would speed up reading by some small fraction. But we don't. But no, I don't care what you do. May I make one suggestion? You're going to have to read these ASTs because you're going to want to do some debugging, which suggests that maybe you want to be a little bit careful with them. And another hint, if you are so clever as to be using Emacs, it has a Lisp mode. And in the Lisp mode, if you have put new line characters into your ASTs at appropriate places, reasonably frequently, you can use Lisp mode to do automatic indentation of your AST. You can just pull the AST into a buffer and say indent this, and it will suddenly be pretty printed for you, all automatically. Know your tools; they will work for you. Okay, questions? Other questions? We're going to go into something completely different now. We're going to move out of parsing and turn to a completely different subject, which is static semantics. So, so far, what we've done is to convert a textual representation of a program into a tree representation. Why? Well, because that's generally more convenient for later processing. The operands are immediately to hand. You can access them in any order you need, as many times as you need. And furthermore, we have eliminated a whole bunch of errors that would cause non-well-formed trees. So we can go into the rest of the compiler knowing that we have a well-formed tree. It may not make any sense, but it's still well-formed. And what we're going to do now is, or at least in our version, is to decorate this tree with a bit more information and to do some analysis of it, to do some further checking to make sure that it's legal, and also to supply or to extract additional information from it and make that additional information available to the rest of the compiler, which is namely the part that generates code or possibly that executes it. So that's the purpose of what we call static semantic analysis. Now, it turns out that we could have done, I think I mentioned this, we could do this kind of static analysis that we're going to do in a parser. However, it wouldn't have been a context-free parser. It would have been a more complicated parser. I think I posted one example of how you do that. When somebody asked, what does a non-context-free grammar look like? And I showed you, and you may have noticed it looked pretty horrendous for just doing a very simple thing, which was checking to see whether two instances of an identifier were the same, as I recall. So it gets a horrendous grammar, but you can do it that way. And in fact, one guy did back in 1968, and the result was that the language that he used, the language that he described, has never been used since. So we don't do that. It's not very good. There aren't very effective tools for doing it that way. We use a separate, but and simpler to deal with, but sometimes a little bit ad hoc way of doing this. We don't have a good mechanism, a single good, well agreed upon tool for automating this process the way we did for grammars, which is too bad, but there you go. Now, I should say something about what I mean by semantics, first of all. I don't seem to have, I used to have a slide in here, but let's see, do I have a slide? No, I don't have a slide. I think I had one at the beginning of the year. So the main source on that any computer scientist turns to when getting into this subject, of course, is the great Lewis Carroll, author of Alice in Wonderland and Alice Through the Looking Glass, because he did all kinds of interesting things with nonsense. But semantics deals with, so you have Humpty Dumpty, when a word means what I say it means. And you have that poem, The Jabberwocky. Remember that? 'Twas brillig and the slithy toes, did gyre and gimble in the wave, all mimsy where the boar grows, and the mome rats out grave. Well, so there is a sentence, and Alice actually remarks on this in the book. There's a sentence, and it sounds like it ought to mean something, but it doesn't. At least not until you fill in meanings for the words. So it has the structure of English, but it doesn't have any sense to it. There are other examples that use English words that don't have much sense. For example, a very famous one is colorless yellow ideas sleep furiously. Colorless yellow ideas sleep furiously. Well, the problem is that, first of all, of course, colorless and yellow is contradictory. Colorless and yellow, and color does not modify ideas. Ideas don't have color. They don't sleep. And you don't sleep furiously in any case. Or at least it's not clear how that could possibly be. So this is a meaningless sentence, but it has all the right structure for an English sentence. So it would pass parsing, but it wouldn't pass static analysis. Okay, so that's what, so semantics refers to the assigning of meaning to a program. What do these things mean? What does every piece of this program mean? What does it refer to? We distinguish, you'll see these terms, static versus dynamic, in a number of contexts. In this context, what we're referring to are properties that are determined purely by the text of the program, independent of any execution of it. Things that, in principle at least, you could extract from just looking at the program itself. These are static properties. On the other hand, there are also properties of the program that have to do with how it reacts to data, how it responds when you give it a certain piece of data. And this we refer to as, dynamic properties. So here's an example. In this particular example, we say that the fact that both of those x's refer to the same entity is a static property of that program. It follows from the scope rules of Python that the x that x plus 1 refers to is the same as the x that's declared in the enclosing function. That's just the way the language is constructed. Now you have a dynamic property. For example, the question of whether x/y is going to raise an exception depends entirely on what the value of y is at runtime. So statically, you can say if the value of y isn't 0, then it will not raise an exception. But the question of whether it actually does raise the exception, obviously, is a dynamic property and cannot be checked. In particular, cannot be checked at compile time. So, and this leads immediately to this problem, as you see in this next example here, that I can figure out from these two things. It is in fact a static property of this program, of these two statements, that x and y will end up being integers or numbers of some kind. That's just the way it is. Or assuming that is, well, yes, assuming that we aren't in a statically typed language in which x is not declared to be an integer, we can tell in a dynamically typed language that x and y are both going to be integers. And this is a source of continual confusion. For example, a lot of people will ask me questions like, should my parser reject x times, or something like string plus list? You know. So, quote ABC, unquote, plus bracket 1, 2, 3, end bracket. Should I reject that? And I mean, you can tell by just looking at that expression that it's wrong, but on the other hand, there's something, at least I think it is, maybe Python will cleverly convert the string to a list, but I don't think so. But on the other hand, the thing is that, okay, fine, you can find that error, but it's kind of, but that's kind of a half-assed job, because you won't find the error x plus y, where x has just happens to be a string and y just happens to be a list. So once you go down the road of attempting to find out whether string plus bracket is in fact erroneous in the parser, you have to go a very long way. And in fact, you even have to, with a dynamically typed language, you have a real problem on your hands doing that in general. And the rule, and sort of there's this, I guess, aesthetic principle of design that says, well, gosh, if you can't do a good job of something, if you can only do really a tiny piece of the job, then, and you can't even describe very well what your limitations are, then maybe it would be better to take some other approach, and that's essentially what we do. So what's going to happen here is, in this particular example, is that if we were compiling Python, we would simply leave it to the runtime to figure out, or to use the fact that x and y are integers. We wouldn't necessarily do anything with that information. Although, one of the possible projects for Project 3 is to do something clever along these lines, but it's not something that's easy to get away with. So the problem, but the problem is, therefore, what happens in many programming languages is that we is that we give explicit types to things for the purpose of being able to check things like this, to check that these expressions are correct. That's the Java philosophy. So if you write something in Java, if you write an expression in Java, a statement in Java, then the statement, at least, it makes some kind of sense. And that is to say, you know that the operators in question will be applied to things that they are supposed to be, of the types that they're supposed to be applied to. So plus will be applied, for example, to integers, to a couple of integers, or a couple of numbers, or something like that. Or it will be applied to a string, to a couple of strings, but it won't be applied to illegal combinations. You know this at the time. The compiler is able to determine it because you declare what the types of everything are. And that's one motivation for requiring it, is that the compiler can check exactly these things. So, what we're going to be doing in semantic analysis is we'll be determining things like this. So, first, we'd like to be able to tell later parts of the compiler, when they see an identifier, what does that identifier refer to? Is it the same thing as this other identifier, or is it something different? Is it a function parameter? Is it a variable? Is it a field in a class? What is it? Another thing that a semantic analyzer might want to do, to the extent that it's possible to do so, is to statically determine what the types of things are. That is, can you, from the program text, determine what the type of this variable right here is? Now, that's obviously valuable information as far as the compiler is concerned. I mean, in the old days, for example, the main reason for having types at all in, say, Fortran was that the compiler needed that in order to produce anywhere halfway decent code. Since at the time they were competing against assembly, like the macho programmers of those days coded in assembly language or possibly machine language. And convincing those people to move to Fortran, well, they would use as an excuse the fact that the Fortran compiler didn't produce as good code as they could with their hand optimizations. That situation actually changed. It turns out that when you're writing any sort of a large program, the Fortran compiler can generally beat you because it has the patience to uniformly apply its algorithms to the entire program, whereas you only have patience for a few critical points. So in those days, types, this is the purpose of types, and in fact, they went to some lengths in the original Fortran to make sure that you didn't have to say anything about types, because that was unnatural. They were only good for the compiler. They weren't any good for you. So, and as a result, they had these rules that said you don't have to say whether these are integers or doubles. If they start with the letter I through N, they're integers, and if they don't, then they're doubles, or they're reals, I should say, floating point numbers. See, that's easy. Then you don't have to say any types. You don't have to think about types. It just all works. And the compiler can use that information. And then, as you know, things changed, and now knowing the types of things is useful because it helps you find errors in your program. It helps you understand your program better. Okay, so another thing that the static analyzer might do is mogrify the tree a little bit in ways that were inconvenient to do at the time you were parsing. Now, this is sort of an ad hoc thing. It occasionally happens. We'll get into it if we encounter it. And then, of course, finally, you're interested in finding errors. So types, scope, that is name binding, and possibly a little bit of redacting of the tree. These are sort of principal activities of the static analyzer. I have to explain that when I say types, well, there's a lot of information that goes into that. One of them is not just telling what the types are, but telling whether expressions use them properly, whether they're used in the right contexts. That's also very important. So what do you find? Well, you'll find multiple declarations. You'll find things that are declared more than once, things that are undeclared. You'll find things that these things will find cases where variables do not have the same type when they should, like assignments and things like that. Find places where you've got procedure calls with the wrong types of arguments, the wrong number of arguments. That's another type error. And then occasionally they'll do some rather exotic things or more exotic things. You see more of this these days. Java introduced this notion of definite assignment. How many people know what that is? How many people have had definite assignment errors in their programs? You probably have. The error where it says you may not have assigned to this variable before it is used, that's the definite assignment error. Java requires that well, the intent of the requirement is to make sure that every variable every simple variable, every scalar variable, no, every simple variable is assigned to before it is used, is assigned some value explicitly before it's used. Now, this is in some sense redundant because Java also tells you what the initial value of every variable in your program is. It's part of the spec. But they put this in on the assumption that that very often a failure to initialize a variable is an error. Now, the problem with this is that the Java compiler can't tell whether something is assigned to in general, because doing so requires solving the halting problem. If you say, sort of, it requires solving the halting problem, sort of. So it gets conservative about this. It says, well, we'll throw out some programs that actually work on the grounds that we can't tell whether this thing is definitely assigned, and so we'll err on the side of caution. For example, the program that says, if this program halts, then x equals 1, semicolon, printf, or system.out.print x, that will cause an error on the grounds that the compiler will simply say, well, I'm not going to figure out whether this function program halts always returns true because that's too hard. I'm just going to assume that sometimes it returns false. And in that case, x won't be initialized, so boom, I'll give you an error message. That's an example. That's conservative analysis of the sort that semantic analyzers we'll see this happen in the future as well. So here is, okay, before we get into this, why don't we I think this would be a good time to take a break. So has anyone thought of some questions to ask about either, well, this material is kind of early on, but maybe some project questions? No. Okay. Well, I make myself available. We're seeing worrisomely few project questions. In fact, I got a remark from a student recently. He said that he was worried that people were not asking questions. He was expecting to be able to come and see all the answers to the questions he had already posted on the news group. And instead, nobody seems to be asking questions. So I think things are going to be really hectic on Tuesday, aren't they? Tuesday, Wednesday. Yeah. I think I'll take a vacation. All right, fine, let's take a break. Yeah.
I don't know if this was a big question, but my group and I were having problems getting the .cc files, basically putting different types of trees in different .cc files instead of having them all in apac.cc. Is there anything special we need to do, or is it just...
You have to make sure that well, generally these are going to be things that inherit from tree.
Yes. From
so most of the program doesn't have to know about them, right?
Okay. Yeah.
I mean, right? That's the way you usually do it in
Yeah.
these cases. You have these virtual methods at the top, and anyone who has to deal with any object that it has just uses those virtual methods.
Yeah.
Okay, so what you need to do is to make sure that the base classes declarations are in .h files, and that you include those.
Okay.
And you also have to make sure that you modify your make file so that it knows that those files exist and
There's nothing
compiles
else
them.
within Horn to get it to use other .cc files?
Oh no, Horn isn't concerned with compilation. Horn produces .cc files. That's
Okay,
it.
okay.
Yeah,
And then-
you take it from there.
And then the gmake file takes all the .cc files.
That's right.
Okay.
So you just have to make sure that every time you add a new file, you go into the list of object files in the make file and use that. It's actually quite automatic. The other thing you have to do is make sure that you get dependencies for that file. In fact, I should mention that because I think some people have not. I have this dependency computation in the newer skeleton, and it's useful for not making mistakes.
Okay.
Yeah.
Thank you.
Yes.
You said you run the autocreator usually a few days earlier. Do you know when that it would start?
I don't know. Tuesday maybe.
Because you also said you might not run it right before the deadline,
No, I don't run it again until the deadline.
so that you might start on Tuesday, but
I run it on Tuesday, then I turn it off
I see. You leave it on for a day or so.
an hour or so.
Hour.
And I try to capture everyone who's submitted, say, a couple of days in advance. I capture all of that, and then I run it again.
Okay, but you'll announce it beforehand so we know to submit what we have. Or I guess,
Well, you should. I mean, why should it matter? Every time you commit, you can
or are you running on the tags
you
directory?
can you run on the tags directly. So just remember to tag things every day.
Oh, okay.
It'll be all right before midnight. Yeah.
We were trying to figure out a way of storing our line number in the tree.
Uh-huh.
While using the hot operator.
Okay. You realize that most of this is done for you. I mean, so now there's a function that will take first of all, your nodes store all their children. So, yeah, if you've got that's interesting. So, if you ask for the location of a node, it will ask the children of the node, right? And they'll tell it. If you're, now this suggests a change to the framework. I should probably make.
Because you know
The
the
other-
function you added in break 1.2, the one that if you give it a location, it returns .st, right?
The recurrent turns are what?
The function you made, the YY something location. That,
Location line, yes.
Yeah, that one. We can't use that in our tree file because it's only using the horn file, right?
Oh, but you can. I'm sorry. There's an example in. I think in the example we give, there's a declaration of. I think the arith example. There's an extern declaration of YY external token of YY printed location or something like that. You can put that declaration into your file.
And then we can call.
And then you can call it. It's an external function, so you can link to it.
Okay.
Yeah, that's good. Yes.
Okay, our question is about our test cases.
Uh-huh.
And for okay, so we have the Python files and then the .std files, but we were wondering, we also need to somehow make a AST file. And is there
Why do you need to do that?
well, to check the output of our compiler versus
Uh-huh.
what it should look like?
What the AST file should look like? I mean, you can do that if you want, but you don't have to.
So
I mean, the whole point of taking these things and unparsing them is to see whether you get back a Python program that does the same thing as the original. And if you do, then even if it's a different program, then you have preserved the semantics of the program.
But I thought our output was in AST.
Yes.
I don't understand how we make that into a program or
Py on parse. Py on parse.
UIN parts.
Well, I mean, there are several things you can do. You can create ASTs from your program, check them by hand once, and then sort of make them permanent as your standard thing, and compare against ASTs. Or, alternatively, you can make carefully constructed Python examples that test the various features that wouldn't work if you were producing incorrect ASTs. Wouldn't work in unparsed form if you're creating incorrect ASTs, and then run those. Now, I forget what I did in the skeleton. Well, I'd have to go back and look to see what the skeleton, which one the skeleton.
There's a way to read AST files and run that as a Python program?
Yes,
How would we do that?
Py on parse.
UIN plus?
Yeah,
Oh.
that's what it's for.
Oh.
Okay. Yeah. All right, let's continue. Yeah, I hope, by the way, at some point in the past, I updated some time ago actually, I updated the Project One skeleton. I said I put some stuff into the make file to automatically generate dependencies. That is, things that tell you to compile this file, you must have these files, or they depend on these files. So if you haven't integrated that into your make file, you might want to do that. It's kind of useful. As you add new files to your program, to your project, do be sure to add them to the make file also so that it knows to compile them. So I think a number of people have had this problem that, it doesn't see my blah, blah, blah. Well, it doesn't see it because you never told it about it. So just keep that in mind when you're doing this. All right, so let's take a look at, a sort of a sample of what a semantic analyzer might do. So we give it this parse tree, which is basically, this abstract syntax tree, which is basically this thing in black, the black parts of the thing on the right, that come from this program. It might look like this. This isn't quite what our AST is like, but it fits on the page, so it fits on the slide, so we'll use this. And so imagine that this is what we get, and so now the question then is, how might we decorate this? Well, we see all of these X's and Y's in here. What do they refer to? They refer to some variable, and what is it? Well, let's take a look here. What information might we want to gather? Well, for one thing, there are two different X's in this particular program. The one at the outer level, X equals 3, and the formal parameter of F. So one of the things we might want to do is to make it clear which one is which, or which refers to which. So here, for example, I have decorated each X with a little decorator, that's the number thing. And these refer to, so this first X is some variable, I don't know what its type is, I'll just call it type any. We haven't really talked about types here yet. So I'll just say it's some type. And it's not nested inside any function. I'll just throw in that information. We'll use that actually later. The runtime will need that information later. We don't need it right now. And here is another x, here, x number 3. It also has some unknown type, and it's nested inside a single function. So it's one level down. It's one nested variable. So I'll record that information. I could have recorded a lot of other information as well, but this is the kind that's useful. And also I have this function. This is f, and I know that because this is I know from the fact that it has a single formal parameter and that it's a function, that its type is going to be any to any. And it has, and again, it's not nested inside any other function, so it's nesting level 0. So I have decorated all of these variables here with things of this kind. I've decorated the expression nodes like plus and so forth with the type of variable, the type of value that they return. And the result of this is now a bunch of useful information that will be used by later parts of the compiler. So that's what you've got here, basically decorated tree that gives us scope information and type information. This being Python, of course, the type information is particularly weak, but you can imagine that if this were Java, there would have been a declaration for x giving it type integer somewhere over here, and there'd be another node that pointed at that x and that included that type in this information. So I'm just going to call these little red things, I'm going to call them symbol entries because classically these things are held in a data structure called a symbol table, so I'll just call them symbol entries. We just, there you go. That's basically all that we have to say to it. We decorate everything with either one of these symbol entries, or we decorate expressions with their types, so that at any point the compiler knows the types of its operands, what little information it can get in the case of Python, and it knows the meanings of all the symbols, or at least what they refer to. Okay, so that's basically it. Pretty straightforward sort of thing. It requires a bit of complication. So we can't now, again, in dynamically typed languages such as Python, dynamically typed meaning that the type of a variable is not fixed, there's not very much that we can say about things like is it going to be all right to take the .x field, for example. You can't say that in Python, in generic Python. You can say a little bit more about it in our dialect, but not in generic Python. Whereas in other languages you can. When you attach type information to a variable, like what class it is, you automatically include, in effect, you automatically tell the compiler whether it's going to be legal to say .x or .y. So we would, so in a statically typed language, it would make sense to include entries for classes that list their fields and the types of those fields. All right, so now a little bit of terminology. This is terminology that applies to programming languages, not necessarily trees, but to programming languages. We're going to refer to the scope of a declaration. The scope of a declaration means this is at least as I'm using it here, a static concept. No, not necessarily. In a statically scoped language, it is a static concept. It refers to that portion of the program that a certain declaration, in which a certain declaration governs the meaning of an identifier. So, and depending on what kind of language you've got, this may either be a section of the text of the program. If you're executing one of these statements, then X means such and such. Or it might be a period of time during the execution of the program. Between this point and this point, the variable X refers to such and such. Depends on how you're doing. It depends on the semantics of the language. I'm also going to introduce the term declarative region. These are basically things that bound scopes. So, for example, the body of a function is a declarative region. The scope of variables inside that function generally is bounded by the function body itself. So we call that function body a declarative region. Now, then this leads us to the two different concepts: statically typed versus statically scoped versus dynamically scoped. So if the language allows you to point to any point in the text of the program and say, whenever this is executed, X has this type, or X means this. This X refers to the same thing that X refers to. Then we say that language is statically scoped. So Scheme is statically scoped. Java, C, these are all statically scoped. Python is statically scoped. Almost all languages are, an exception being some of the earlier versions of Lisp, and some of the scripting languages are not statically scoped. So in other words, if you're in a language where the meaning of a variable depends on what the execution was just before it. Was I executing this piece of code that redeclared this variable, or was I executing that piece of code which didn't? Then if that's the case, then we say the language is dynamically scoped. You cannot tell just by looking, in general, you cannot tell by looking at where the variable is in the program. You cannot tell what it's going to mean, because it could mean different things depending on the data to the program. All right. So the thing about scope and declarative regions is that the same variable name can apply to different things. So depending on where you are in the program, the variable might mean various things depending on which declarative region you happen to be in at the moment. And an example of this, well, you know examples of this. You can have classes that have the same field names even though they have drastically different types. There are also you also find examples in Java and C++ of cases where you reuse the same name, but because they're referring to two entirely different things, there is no conflict. Do you happen to know an example of this? So I use the same name in Java to refer to two different things in the same class or function, and there's no confusion except maybe to the programmer, because these things are used in two different ways. Seen anything like that? Ever heard of that? I'll let you think about it, because the weekend is upon us. So keep those questions coming, folks. And those bug submits, and I'll see you on Monday.